Hello, I'm Maurice Dupre, and in this section we're going to discuss indefinite integrals and the substitution rule. Let's begin by looking at the definition of the indefinite integral. The indefinite integral looks very similar in notation to the definite integral. It's just that there are no limits on the integral sign. So when you see integral f of x dx, that notation stands for the set of all antiderivatives of f. That means it always includes an arbitrary additive constant, and it's traditional to denote as capital C. So this is therefore a symbol for all real numbers, because notice any real number is an antiderivative of 0. If I differentiate a constant, I get 0 no matter what the constant is. So consequently, when I do the indefinite integral of 0 dx, I get the antiderivative 0 plus the arbitrary constant c. Well, 0 plus c is c. But remember, this is now to be taken as the set of all antiderivatives of 0. Well, that would mean c is the set of all real numbers. Well, let's look and see how this works in a couple of simple examples. So, for instance, if I write the antiderivative of x squared dx, well, we recognize that x cubed over 3 is a function whose derivative is x squared. So that's an antiderivative. And so when I add, in effect, the set of all real numbers, I'm getting all possible antiderivatives of x squared. If I said the antiderivative of 1 dx, well, an antiderivative of 1 is x. Add the capital C. That stands for all real numbers, so in effect all functions of the form x plus some constant. Any one of them has derivative 1. So that's the way our notation works. Now in computations, for instance, for definite integrals, remember, to calculate the definite integral from a to b of f of x dx, we begin by looking for an antiderivative. So we can say that's the indefinite integral of f of x dx, and that's to be evaluated between the limits a and b. So our procedure for calculating definite integrals in terms of this indefinite integral notation could be written: the definite integral from a to b of f of x dx is the indefinite integral of f of x dx evaluated between the limits of integration. Well, the indefinite integral, in effect, is the set of all antiderivatives of the integrand, and so consequently indefinite integration is basically anti-differentiation. You anti-differentiate and then add the arbitrary constant. Well, what this means then is anything you differentiate gives you some type of formula for anti-differentiation and therefore for indefinite integration. So all our differentiation rules have counterparts which are anti-differentiation rules, and the first one that we want to look at is the chain rule. It leads to the substitution rule. So suppose capital F prime of u is f of u and u is g of x. Then the derivative with respect to x of capital F of g of x by the chain rule is capital F prime at g of x. Well, capital F prime is little f, so that's little f of g of x multiplied by g prime of x. Consequently, the antiderivative of that expression is f of g of x. Well, if u is g of x, that means it's f of u. In other words, when I differentiate f of u with respect to x using u equal g of x, the chain rule says I get little f of g of x times g prime of x. Now, since capital F is an antiderivative of little f, we can write this capital F of u equals the indefinite integral of little f of u du. And this is what we call substitution. So right here, the g of x is the u, and we think of the g prime of x dx as being the du. So in effect, there's a sort of a substitution going on here. Now notice that g prime of x is du dx. And so consequently, if in this equation I treat the du dx as if it were a fraction and can multiply out the dx, then when I do that, I get the equation du equals g prime of x dx. And so we think of this process as a type of substitution. So the technical condition here is that we have to have u equal g of x as a differentiable function whose range is an interval capital I, and f is continuous on I. Then we can say the indefinite integral of f of g of x times g prime of x dx equals the indefinite integral of f of u du. So that's substitution. Now there's a useful notation with substitution, and it's to remind us what the substitution is. So to remind us that u equal g of x, write indefinite integral of f of g of x, g prime of x dx equals indefinite integral f of u du, and then put the vertical line and write u equal g of x down here, so that what this is indicating is if we want the antiderivative of that expression in terms of x, once we've done this antiderivative in terms of u, we're then going to replace u everywhere by g of x. So after anti-differentiating f of u with respect to u, we are reminded to substitute g of x for u in the final result. Well, let's use the substitution rule to compute some indefinite integrals. Here I want to compute the indefinite integral of the quantity 9r squared divided by the square root of the quantity 1 minus r cubed with respect to r. So what we want to do is try and simplify this integrand by substitution. One thing that would make things simple is if instead of having an expression inside the square root, I simply had a single variable there. And so let's start by trying to set u equal to 1 minus r cubed. Now when I do that, du is the derivative of 1 minus r cubed, that's negative 3r squared, times dr. That is, du dr is negative 3r squared. So now let's solve this expression for dr. dr is du divided by negative 3r squared. So now what we can do is replace the 1 minus r cubed by u and replace the dr by du over negative 3r squared. So when we do that, we get integral 9r squared divided by square root u, because the square root of 1 minus r cubed is now just square root u, and the dr is du divided by negative 3r squared. Notice what happens. The r squares cancel out in this case, so we would say this attempt at substitution has been successful. Everything's in terms of u. Well, 9 divided by negative 3 is negative 3, so we have negative 3, which being a constant can come out. Negative 3 times indefinite integral du over square root u, which we could also write as negative 3 integral u to the negative 1/2 du. Now to find an antiderivative of u to the negative 1/2, well, let's just go up a full power, up to u to the 1/2, negative 3 u to the 1/2 divided by 1/2. If I differentiate u to the 1/2, I will get 1/2 times u to the negative half, and that 1/2 out front will cancel the 1/2 I have down here. So this is the antiderivative with respect to u, and now we're going to substitute back in what the u is. The u is 1 minus r cubed. So we have 1 minus r cubed raised to the 1/2 power. And what do we have out front? Well, a 1/2 in the denominator is a 2 in the numerator. 2 times -3 is -6. And then what we have to remember is to add the big capital C. Let's look at an indefinite integral where we use the substitution rule. Here I have the indefinite integral of theta times the 4th root of the quantity 1 minus theta squared d theta. So again, I see inside this 4th root is an expression in theta, and so let's begin by trying to substitute a single variable for that entire expression. So we'll set u equal to 1 minus theta squared. Now then, du is -2 theta d theta, because du d theta is -2 theta. And so consequently, what I can do here is solve for d theta in terms of du. I can write d theta is du divided by -2 theta. So when I substitute into this indefinite integral, I get integral theta times the 4th root of merely u, because 1 minus theta squared is u. And for d theta, we'll substitute our expression here, du over -2 theta. Notice the thetas cancel out. And so everything left is either a constant or an expression in u. The -2 down in the denominator can come out. Here, we could put it out front as a -1/2. We'll just put -1/2. 4th root of u is u to the 1/4 power du. So the antiderivative will be -1/2 multiplied by, let's raise the power by 1 up to 5/4 and divide by that new power. Notice that gives us an antiderivative with respect to u. If I differentiate u to the 5/4, I get 5/4 u to the 1/4, and so that 5/4 coming out will cancel the 5/4 I've put down here in the denominator. And so next, we want to replace the u by its expression in terms of theta. U is 1 minus theta squared. U is 1 minus theta squared. And so consequently, well, let's simplify these fractions here. The 4 comes up to the numerator. So 4 over 2 is 2. We have -2/5. So consequently, we'll have -2/5 times u to the 5/4, but u is 1 minus theta squared. So we have 1 minus theta squared to the 5/4. And then finally, don't forget to add the big capital C. Let's work an indefinite integral using the substitution rule. Here I have the indefinite integral of 1 over square root of x multiplied by the quantity 1 plus square root x, all in the denominator here, 1 plus square root x, quantity squared, everything there is in the denominator. It looks like a complicated expression, but let's concentrate on the parenthesis, and what's inside the parenthesis, let's replace that by a single variable u. So we're going to substitute u equals 1 plus the square root of x. Well, then du dx is the derivative of this expression, which is simply 1 over 2 root x. And so consequently, du is 1 over 2 root x dx. So multiplying this one out, we see dx is 2 root x du. So let's substitute in. We have the indefinite integral of 1 over square root x. And look, 1 plus square root x, that's just u, so we have u squared. And then our dx is 2 square root x du. So let's put 2 square root x du. And notice the square root x cancel. And so 1 times 2 is 2. That's just a constant. It comes out. 1 over u squared is u to the negative 2. And so we simply have 2 times the indefinite integral of u to the negative 2 du. Well, that's easy to anti-differentiate. The antiderivative of u to the negative 2 is u to the negative 1 divided by negative 1. After all, if I differentiate this, the power negative 1 comes down and cancels the negative 1 I've put in the denominator, and we lower the power by 1, and it goes from negative 1 to negative 2. So there's our antiderivative, and so finally we just have to substitute the 1 plus square root x for u. So 2 over negative 1 is negative 2. U to the negative 1 is 1 over u, and so we have negative 2 over 1 plus the square root of x. Well, what haven't we done? We have to remember, add the big capital C. The substitution rule can be used to simplify integrals sometimes where we could, if we wanted to, do it in a straightforward method. Let's look at an example. Here I have the indefinite integral of the quantity s cubed plus 2s squared minus 5s plus 5, all multiplied by the quantity 3s squared plus 4s minus 5. Now we know we could multiply all this out. We have 4 terms in this polynomial, 3 terms in this, so when you multiply it out, you'll get 12 terms, which you then have to carefully combine. And your chance of doing that without making a mistake might be reasonable if you're real careful. But let's look closely. If I take the derivative of this first factor, the derivative of s cubed is 3s squared. The derivative of 2s squared is 4s. The derivative of negative 5s is negative 5. And of course, the derivative of 5 is 0. So what I'm looking at here is a product of 2 factors where the second factor is simply the derivative of the first. So let's set u to be the first factor, and then we know du is all of this. And so all I have here is integral u du if u is s cubed plus 2s squared minus 5s plus 5. Well, the antiderivative of u with respect to u is simply u squared divided by 2. And so we want to substitute for u the expression s cubed plus 2s squared minus 5s plus 5. And so that will result in 1/2 the quantity s cubed plus 2s squared minus 5s plus 5, all squared. And of course, don't forget the big capital C. It's not always obvious how the substitution rule can be applied when in fact it can be applied. Generally speaking, when we look at an indefinite integral, if it's not something that we see the antiderivative of right away, the first thing to try is substitution. If you can't succeed with substitution, then later on you'll be learning more powerful rules. But let's begin by looking at a problem in substitution where we don't see right away what to do. Here I have the indefinite integral of the square root of the quantity x minus 1 over x to the 5th dx. Notice it's not obvious at all what to try to substitute. Do I substitute u equals x minus 1? Do I substitute u equal x to the 5th? Well, you can try it, but you won't get anywhere with those substitutions. For instance, if I set u equal x to the 5th, then du would involve x to the 4th, wouldn't it? And I don't even have an x to the 4th around here to cancel with that. So consequently, what we need to do is start simplifying this expression inside the radical a little bit. Well, one thing we can do is notice that x to the 5th is actually x times x to the 4th. Now the square root of x to the fourth is x squared, so let's pull that out of the radical. We get integral, and I'll pull it out to the right, square root of x minus 1 over x times 1 over x squared dx. Now let's divide the x into each term inside this radical, and we get indefinite integral of square root of 1 minus 1 over x. Well, I'm going to write that as x to the negative 1 times, and I'll write this 1 over x squared as x to the negative 2 dx. And so now you can see easily in this form what I want to do is substitute u equals 1 minus x to the negative 1. Because when I do, du is simply negative 1 x to the negative 2 dx. Negative 1 is plus 1, so du is x to the negative 2 dx. That is, there's our du, there's our u, and so we have indefinite integral u to the 1/2 du, which is antiderivative of u to the 1/2 is u to the 3/2 over 3/2. That is 2/3 u to the 3/2. Well, what's u? U is 1 minus x to the negative 1, or 1 minus 1 over x, all to the 3/2. And finally, don't forget to add the big capital C. Let's look at a substitution problem where we have an integral of a function involving the natural logarithm. Here I have the indefinite integral of dx divided by x times the natural log of x. Remember, the derivative of natural log of x is 1 over x, and so almost always when you see natural log x in an integrand, you want to look to see if you can find an x in the denominator, and if you can, you probably want to substitute u equals ln x. Let's try it here. We're going to set u equal ln x, then du is simply 1 over x dx. That is, our dx is simply x times du. And so substituting in, we have x du divided by x, and our ln x is now simply u. Notice the x's cancel, and we have simply integral du over u. Well, integral du over u is obviously natural logarithm of absolute value of u. And so consequently, we end up with the natural logarithm of the natural logarithm of x. Of course, we have to put absolute values in there, plus the big capital C. Let's look at an indefinite integral involving the exponential function. Here, I have the indefinite integral of dz divided by the quantity 1 plus e to the z. Well, there's not much that we can try here other than just substituting u equals 1 plus e to the z, so let's go ahead and do that. If I do that, then du is e to the z dz. Well, let's substitute then. Notice that if du is e to the z dz, then dz is e to the negative z du, or du divided by e to the z. So we get integral. Now the 1 plus e to the z of the denominator is just a 1 over u, times du divided by e to the z. Well, notice we don't have everything in terms of u. We have an e to the z here, but look at our equation relating u and e to the z. E to the z is u minus 1. So this becomes integral du over u times u minus 1. What can we do with that? Substitution won't help us now. What we have to do is look at that expression and simplify it somehow. One thing we can notice is that if I add and subtract a u here in the numerator, I can rewrite this. First off, if I break it between the u and the 1 minus u, I can write this as u divided by u times u minus 1 plus 1 minus u divided by u times u minus 1. Notice in the first term the u's cancel and I end up with simply 1 over the quantity u minus 1. In the second term, 1 minus u over u minus 1 is negative 1, so that's minus 1 over u. So you see our integrand has actually simplified. And so that means the integral of du over u times u minus 1 equals the integral of 1 over u minus 1 minus 1 over u du. And now we've got it finished because to anti-differentiate 1 over u minus 1, that's just natural log absolute u minus 1. And then we have minus natural log of u, absolute value. So there's our antiderivative in terms of u. And finally, we want to substitute back in. What is u minus 1? Well, that's e to the z. So this is e to the z. Natural log of e to the z is z. So we have z minus natural log absolute value of u. Well, u being 1 plus e to the z is positive, so we get natural log 1 plus e to the z. And then finally, what's our last step? Add the big capital C. Well, we've looked at the concept of the indefinite integral, and we've looked at the substitution rule and how to use it to calculate indefinite integrals. Remember, the first thing you try to substitute may not solve your problem, but don't give up. Sometimes, if the integrand is very complicated, you might want to try several different substitutions before you reach the answer. Don't give up and try some of these problems on your own.